This video is on the section 2.3 notes, which is family of functions, transformations, and symmetry. So first, I've kind of set up the notation of what this is going to look like, and it might not make a lot of sense at first, and that's okay. As we go through the notes, it will make more sense, and it will be something that you can refer back to. So we're going to say that a parent function with no transformations is y equals f of x. A transformed function, or a parent function that has transformations, is going to look like this. It's going to have a in the front, that's the coefficient, h inside, and then k on the end. And we're going to look at what numbers in each of those positions would do and how they would transform the function, or how they would move the function, how they would adjust the function to maybe make it a different size, or maybe shift it left, right, or maybe reflect it over an axis. So first, we're going to look at the transformation of reflections. So if you have the parent function y equals f of x, then if you see y equals negative f of x, that means the graph has been reflected over the x-axis. It's been flipped upside down. So here we can see this is a regular absolute value graph. The V shape is going up. If you stick a negative in front of the equation, it flips it upside down. Here is a regular quadratic, or a parent graph of a quadratic. If you stick a negative in front of it, it flips it over the x-axis. It flips it upside down. Here we have a cubic graph. You can see it starts over here at the bottom and it goes up. And you can see that each individual piece has been flipped. So the part that was here that was up is flipped down, and the part over here that was down is flipped up. So since we have each piece flipping to the other side, the positive versions are flipping to the negative side. The sides that are negative are flipping to the positive side. You can see that the x coordinates are staying the same. They're staying in the same spot. It's the y coordinates that are changing. You're going from up to down. That's a y coordinate adjustment. So when we want to take a function like this square root function right here and transform it, I'm not going to change the x coordinates at all. I can just keep those. All I'm going to do is take the y coordinates and I'm going to multiply them by -1. So that what was up goes down here, what's up here goes down here. So I'm multiplying by -1 to change all of them. And I already have this graphed because I accidentally drew it in before I started videotaping. So we've got that one drawn. So here is kind of a takeaway message from this. To reflect a function over the x-axis, you must multiply its y coordinates by -1. And then you can do any reflection over the x-axis. Okay, the next transformation is stretching and shrinking. And another word for shrinking is compression. And it depends on which textbook you look at, or maybe which teacher you have, which wording they'll use. So I prefer compression, but since this textbook says shrinking, I'm guessing my math lab is going to use that wording. Okay, so the graph of y equals f of x is going to be stretched or shrunk if there's a coefficient in front of it, if there's a number in front of it. You can tell that it's stretched if that number, that coefficient in front of the function, is greater than 1. You can tell that it's shrunk if that number is between 0 and 1. So we're not talking about the sign of the number. If the number is negative, that just means it's reflected. We're talking about the size of the number. So a stretched graph, you can imagine if you've taken like silly putty and you stretch it, it makes it taller, it makes it skinnier. If you take maybe a hamburger that has a bunch of toppings on it and you squish it, you compress it so you can fit it in your mouth, what you do is you make it less tall, but you make it really wide. So that's kind of how stretching and compressing works when you're kind of plugging these points in. You can see it the most clearly on this graph right here. So this red one right here in the middle is a regular square root graph. And if you stretch the graph by 2, it takes this part and it makes it twice as tall. So every individual portion of the graph, whatever the input is, the output ends up being twice as tall. If you stick a 1/2 over there, then whatever the original output was, the output's going to become half of that. So that's how it works. Over here, you can't see the height very well because they didn't give you points to compare, but you can tell that if the red is the original graph, then when you stuck a 2 in front of it, it stretched it and it made it really skinny. When you took the original graph, the red, and you put a 1/2 in front of it, it compressed it, it ended up making it wider. So there's a couple different ways you can see that transformation in action in a graph. So here, we're going to go ahead and do the transformation on this cube root function. And we have to think again about if you have a piece of silly putty and you stretch it, that's a vertical change, right? You are changing the height of the graph. You're making it twice as tall. And so if we take something or we compress it, you might be taking a hamburger that's this wide that can't fit in your mouth and you're squishing it so that it's this tall so then it can fit in your mouth. So if that's something we're doing, that is a Y value that we're changing. It's not an X value because we're changing how tall it is. So I'm going to keep my X values the same. And here I see that my stretch was 2. It's a vertical stretch of 2. And so I'm going to take all of my Y coordinates from the parent function and I'm going to make them twice as tall. So -8, -4, I can't graph. -1, -2, 0, 0, 1, 2. And if you want to know kind of what it would look like, 6, 7, 8, 8 would be over here, 4, you could kind of put those other points in and just draw them off the way that I did so you can see what it would look like. I probably should have made the grid with different intervals to make it easier for you guys, so I apologize for that. So that's what that graph would look like. So to vertically stretch or shrink a function, you must multiply its Y coordinates by A. And A is that number, that coefficient in front of the function. Now there's a note here. It says if a function is reflected over the x-axis, so it's got a negative in the front, and it's vertically stretched or shrunk or compressed, you can perform both of those transformations at the same time. So if you happened to have a -1/3 in front of the function, then that function would be reflected over the x-axis and compressed to be 1/3 of its height. It would have both of those. And to do that, you could just take the Y coordinates and multiply by -1/3. You could do both at the same time. Okay, the next transformation is a shift left and right. So this is talking about the H value. You can see that's the inside of the function. So if the function had parentheses, it would be inside the parentheses. If it's a square root sign, it'd be inside of the square root. If it's the vertical lines of an absolute value, it would be inside those vertical lines. So they translate H units to the right and H units to the left, and we're going to see that it's a little bit backwards from what we think. So here is the original quadratic, and x plus 3 squared moves it to the left. Here we have the regular square root function. Square root of x minus 3 actually moves it to the right. Square root of x plus 3, or actually x plus 5, moves it to the left. Here's our absolute value function. We have absolute value of x, that's the gray one. And then when it says absolute value of x minus 1, it shifts it to the right. So it's always kind of the opposite of what you would think. So this graph right here, it says parentheses x plus 2 cubed. Since it says plus 2, this would be shifting to the left 2. Now in this case, since we're shifting to the right and the left, we're going to be adjusting our x coordinates. So I'm going to copy the y coordinates. Those are going to stay the same. And to shift the x coordinates left 2, I'm going to take each x coordinate and subtract 2. So -4, -3, -2, -1, and 0. -4, -8 doesn't really fit. I guess I can draw it though. 1, 2, 3. It's down here somewhere. -3, -1, -2, 0, -1, 1, and then 0, 8, 6, 7, 8, somewhere up there. So the graph would look something like that. Okay, to horizontally shift a function, you must add or subtract the opposite of h to its x coordinates. Add or subtract the opposite of h to its x coordinates. So I can see there was a +2 here, so I did subtract 2 from the x coordinates. So I did the opposite of +2. Okay, let's look at the next one. This is a translation up or down, and this has to do with the number on the very end of the function, the number that's added, the k value. And this is exactly what you would think it is. If that number is positive, x squared plus 2 takes the graph and shifts it up 2. X squared minus 3 takes the whole quadratic function and shifts it down 3. Here's a square root graph. Add 3 on the end, it moves it up 3. Subtract 5 on the end, it moves it down 5. So here, this is an absolute value function with a -5 on the end. This is going to shift the entire graph down 5. And if we think about which coordinate should be adjusted, if we're moving up or down, that's going to be a y coordinate change. So I'm going to keep the x coordinates the same. And I'm going to shift all of the y coordinates down by 5 by subtracting 5 from each of them. So -3, -4, -5, -4, -3. And then I can go ahead and graph each one. So to vertically shift a function, you must add or subtract a value of k to its y coordinates. Okay, so this is kind of a summary of what we just learned. In the front, if you have something here, this is a reflection over the x-axis, if it's negative. And then if this number is greater than 1, it's a vertical stretch. If this number is between 0 and 1, it's a vertical shrink or a vertical compression. And you multiply the number to make that transformation happen. If it's one of these numbers, then you would add or subtract. This shifts the graph to the left and right. This shifts the graph up and down. Left and right, up and down. And you would add or subtract to the coordinate. Here we can see that any transformation that happens kind of on the outside of the function is going to change the y coordinates. Any transformation that happens on the inside of the function happens to the x coordinates. Okay, so we're going to go ahead and we're going to put all of that together. So here, I'm going to kind of make a list of my transformations for this example right here. We have a negative in the front, so that negative in the front means that the graph has been reflected over x. The 2 means that the graph has been vertically stretched by 2. The -3 means that the graph has been shifted to the right 3. So the inside of the function is kind of the opposite of what you would think. A minus actually means right, not left. And the plus 4 on the end, it means the graph has been shifted up 4. All right, now the one in the front, so this -2 in the front, those are transformations that are multiplied. These 2 on the end, these are transformations that are added or subtracted, okay? The transformations on the outside of the function, -2 multiplied in the front, 4 added on the end, those happen to the y coordinates. The transformation that happens inside the function, inside the parentheses, that happens to the x coordinate. Okay, so first what I'm going to do is I'm going to start, I always do my transformations from left to right. So I'm going to start with the a value, -2. I remember that little note, we can do the reflection over the x-axis and the vertical stretch. We can do that at the same time. So that happens to the y coordinate. So I'm going to keep my x coordinates the same. So since this was a quadratic, that means that this is the table from y equals x squared. That's what this table is from, and I just got it from some of my previous notes that have the table in it. All right, and so what I'm going to do now is I'm going to reflect over the x-axis by multiplying my y coordinates by -1. I'm also going to vertically stretch by multiplying my y coordinates by 2. So I'm going to multiply by -2. -1 and 2 at the same time. That's going to reflect over x and stretch by 2. So -8, -2, 0, -2, -8. Okay? Next, I've got this transformation's done and this transformation's done. Next, I have that the graph is going to shift to the right 3. So that's the +3. It happens to the x coordinate, and it is a change that you do by adding or subtracting. So shifting to the right 3 means I'm going to take all my x coordinates and add 3. So 1, 2, 3, 4, 5. And I did add 3. Okay, and then for the last, I have the +4 on the end. This happens to the y coordinate, and it's something that you do by adding or subtracting. It's shifting the graph up 4, and so I'm going to add 4. So +4, +4, +4, +4, +4. Okay, and now I can graph my transformed function. And I can kind of think through, did all the transformations happen? Is my graph upside down? Yes. Does it look twice as tall as normal? Yeah, it looks pretty tall. Did the vertex shift to the right and shift up? Yes, it did. So it has all of the transformations that I expected to see. So check, I did the right 3. Check, I did the up 4. Okay, let's try another one. Now, this one, they'll do this sometimes in the book, and I hate it when they do this, but I did this in our notes because it's a common enough thing for math problems to do. But they kind of wrote things out of order, and I hate when they do that because I think it looks weird. So I'm going to go ahead and fix it. Y equals 1/2 x plus 1 in an absolute value symbol with a +3 on the end. Okay. So I would say pause the video, see if you can figure out what each of the transformations are. I can see 3 of them. All right, so the first transformation is the 1/2. This is going to be a vertical shrink or vertical compression by 1/2. The graph is going to be half as tall as normal. It's going to look wide. The graph has shifted to the left 1. The graph has shifted up 3. Okay, Now we're going to do the transformations one at a time. So what I want you to do is use this table to do only one transformation. You're going to shrink the graph by half. Think about, should you do that to the x coordinate or the y coordinate, and how do you do it? Shrink the graph by 1/2. Go ahead and pause the video and try it. Okay, so to shrink the graph by 1/2, we're going to keep the x coordinates the same. And I'm going to take the y coordinates and multiply them by 1/2, or cut them in half. So 1, 1/2, 0, 1/2, 1. Okay? And this is a vertical shrink by 1/2. Okay, so I did that one. Next, I have to shift the graph left 1 and up 3. Go ahead and pause the video and see if you can complete the table to go left 1 and up 3 for each of your points. All right, so to shift all my points left 1, I need to take all my x coordinates and subtract 1 from them. So -3, -2, -1, 0, and 1. That is left 1, okay? And then to shift all the points up 3, I just need to add 3. So 4, 3.5, 3, 3.5, 4. Okay. So -3, 4, -2, 3.5, -1, 3, 0, 3.5, 1, 4. So this V is pretty wide and pretty short compared to what we're used to. So I can see that it's compressed, short, wide. It has, the vertex here has shifted left and shifted up. So it appears that the transformations are there and they make sense. Okay, next we are going to talk about whether a function is even or odd and what its symmetry is. So the definition of something that is symmetric about the y-axis is if you can take the graph and fold it on the y-axis, here's your y-axis, fold it on the y-axis and you have the same picture on each side. So that's one way you can see. If that is the case, then you have an even function. And another way that you can see is by actually plugging in -x to the function to see what happens. So this is our function, f of x equals x squared. And if I take this function and plug in -x, I end up getting -x times -x. That's what x squared means. And that gives me x squared. -x times -x is just x squared. So what they were saying here is that f of -x is identical to f of x, and you'll notice that that's true. F of -x is x squared, f of x is x squared. So if a function is symmetric about the y-axis, then it is also an even function. You can see it visually by looking at how you can fold the graph over the y-axis. You can see it algebraically by plugging in -x and simplifying the function to see what happens. Okay, let's look at this one next. This is symmetric about the origin, and this is a little bit harder to demonstrate because you're not picturing folding a paper, you're picturing spinning it. So I got another one. Okay, so if it's symmetric about the origin, what that means is that I can take the graph and I can spin it like this, and I didn't spin it a full 360, I only spun it 180 degrees. You can see my numbers here are upside down, but it looks identical to the graph that I had. And that is what symmetry about the origin is it's rotational symmetry. It means you can spin the graph 180 degrees and it looks the same. So I started with my function like this. I'll put a little smiley face so you can see there's my orientation there. And if I take this and spin it about the origin, my pencil's at the origin, I can spin it 180 degrees and the function looks exactly the same, but I've only spun it 180 degrees. I haven't spun it all the way around. So that's what symmetry about the origin means. If that's the symmetry that you have, then a function is odd. So if we have an odd function, f of x is x to the third, is the graph that we're looking at here, then the way that you can check that odd function algebraically, or check to see if it's symmetric about the origin algebraically, is you can plug negative x in, and it's going to be different than what we saw before. What we saw before is you get the exact same function. Here you don't. Negative x times negative x times negative x. If you multiply a negative x 3 times, you get a negative answer, and you get x to the third. So you end up getting the negative version of the function. And that's the definition of an odd function right there, is that if you plug in negative x, you get the negative version of the original function. All right, so that's how you can solve for it algebraically. So what we're going to do next is we're going to look at a few examples and just determine their symmetry. Another way that we could describe these examples is, instead of saying discuss the symmetry, we could say determine if they're even or odd. The procedure would be the same. So we don't have pictures of these, we only have the equations, which means we have to do these two algebraically. We have to use the method where we plug in negative x and see what happens. So plugging in negative x, so here I've got 5 times negative x to the third, and that's 5. Negative x times negative x times negative x, we know, we just did it, is negative x to the third. Over here I have minus minus x, so that's plus x. 5 times negative x to the third is negative 5 x to the third. And if I compare this to the original problem, I could factor out a negative, and then I see if I take out a negative, it's the exact same as the original problem. So the negative version of the function, here's the function, here's the negative version of the function. That means that my conclusion here is that this is an odd function, but that's not what they asked. They didn't say is it even or odd, but they could have. They said find the symmetry, and so this is symmetric about the origin. It's an odd function, so it's symmetric about the origin. Another way you would have been able to see that is by graphing it. Okay, let's look at this one. So g of negative x, we're going to plug in a negative x and add 3. Now with an absolute value function, it doesn't matter if I put a negative sign in there with the x. No matter what ends up happening here, it's going to give me a result that's positive. So this is going to be the same as the absolute value of x plus 3. And nothing changed about the 3 because I wasn't plugging in an x there. So this is the same as g of x. G of negative x and g of positive x, they end up being the same thing. This is also g of positive x. And so I would say this is an even function. If they asked me, is this even or odd, I'd say it's even. But they didn't ask that. They asked about the symmetry, so I'm going to say it's symmetric about the y-axis. All right, here I'm going to plug in the negative x and see what happens. So negative x times itself is x squared, minus 3 times negative x is positive 3x. So I can see this is not the original function. I can take out a negative, it's not the negative version of the original function either. So we would say this is neither. It's not even, it's not odd, it's neither. Which when you're thinking about numbers, it's like, well, it has to be even or odd, that doesn't make sense. But if we think about symmetry, all this means is that this graph is not symmetric about the y-axis, it's not symmetric about the origin. So we just say it doesn't have symmetry like that. It might have another type of symmetry, but not the y-axis, not the origin. And so in terms of functions, it's not even or odd, and it's okay for that to happen.